Okay, so the topics now becoming more interesting, and now we'll talk about more complicated analysis, which is about spatial mechanisms. In the first session, I talked about the difference between planar, spherical, and spatial mechanisms. Where planar, all the parts or all the mechanisms are moving in parallel uh, planes, basically, and spherical is more like parallel or perpendicular, basically, planes, and or spherical planes also could be called. And spatial mechanism is the general case where actually all particles or parts are moving in non-parallel or nor spherical planes, which is representing actually robots arms, for example. They move in more like spatial mechanisms. Now, spatial mechanism, of course, can be analyzed only in 3D, unlike planar, because the planar they are moving in one, or actually on one or parallel planes. That's why it can be analyzed in 2D. Now, we talked about mobility, and the mobility that we talked about before uh, was applied on planar mechanisms, so in 2D mechanisms, and now let's talk about 3D. Now, if you remember when I talked about mobility in 2D, I said that link or free link in a 2D plane has the beginning 3 degrees of freedom, where the first degree of freedom is basically moving along X or translating along X. The second is translating along Y, and the third is rotating around Z. Now, in 3D world or 3D space, free link at the beginning has 6 degrees of freedom. And these 6 degrees of freedom, they represent translating along X, Y, and Z. So it can translate along the three axes. And it can also rotate around the three axes. So it can rotate around X, Y, Z. So it has completely freedom in the 3D space. And this is why it starts with 6. So like in the formula for the 2D degree freedom, we start here with the total degrees of freedom of free link multiplied by the total number of links, of course, minus 1, which is always our frame, which is the base. Now, after that, exactly also the same as before, we start to add or start to actually to reduce the velocity or constrain the velocity, velocity, the degrees of freedom, or actually mobility as also called, by considering the different number of joints we have in a mechanism and how many of them. So we have here G1, 2, 3, 4, and 5. They represent basically 5 types of joints. Starting with the first type, with the G1 is actually multiplied by 5. That means, considering that at the beginning I have 6 degrees of freedoms, or degrees of freedom in 3D space, if I have a 5, that means I'm constraining 5 of them and keeping only 1. That means J1 represents joints that have only 1 degree of freedom, like the standard joints, the revolutes, or prism, for example, that are the common joints. Now the rest would be just by difference between 1. For example, here, joints that they have 2 degrees of freedom, like cylinder, because in cylinder you can rotate and translate or slide. And here, joints that they have 3 degrees of freedom, and that we like the spherical joint, because it can rotate along X, Y, and Z. And here actually minus 2, they have 4 degrees of freedom, and here they have, of course, 5 degrees of freedom. Now actually, as I said, in robotics in general, these are the most common. You might get to this one in some cases. This is now less let's say common or rare here, and the rest are actually really rare to be used, and I haven't seen that they are used in robot arms, for example. But anyway, this is general formula for estimating or calculating the mobility or degrees of freedom for mechanism in 3D space. So if we take this mechanism here, we have basically, it's quite strange mechanism. As you can imagine, we have, this is a frame and this is a frame. The yellow link here actually rotating around the frame 0. The green also can rotate and slide along the frame 0. It's the blue one can rotate and slide along the blue link, and the blue one and basically the green one, they have actually the 2 degrees of freedom, which is cylinder here, this one, which always rotation and translation. So basically we have different cylinders here, 1 cylinder, 2 cylinders, 3 cylinders, and these 3 cylinders, they have 2 degrees of freedom, which are rotational and translation. We have two, or actually we have 1 rotational only, or volute, and the rest are cylinders. So if I apply here our formula, this is a closed loop mechanism, and as I said, when you have closed loop, that means it has 1 degree of freedom, so you need to end up with the 1 degree of freedom. And if you estimate here, actually we end up with 1 degree of freedom because we multiplied 5 by 1, and 1 here represent the joints that they have 1 degree of freedom, and we have actually only 1 joint, which is this one, and we have 3 joints that they have actually 2 degrees of freedom. So this is why I multiplied 4 by 3, and at the beginning we have 18 that represent actually 4 links. So we have here 1, 2, 3, and 4. So our 4 is the base actually. So we have at the end here 6 multiplied by 3, so 18 minus 5 minus 12, and we end up with 1. Now example 2 is a mechanism that we have seen before. We have here 2 spherical joints. These spherical joints, they have 3 degrees of freedom because they can rotate along x, y, and z. We have 2 rotational joints, and let's estimate the degree of freedom. Here we have some special case actually, because we would end up with, if we apply the formula, we would end up with 2 degrees of freedom. But this mechanism, as it's a closed mechanism, it can be moved only with 1 actuator or motor. That means it has actually 1 degree of freedom, but the formula is giving me 2 degrees of freedom. Now, the reason behind that, there's something called idle freedom, which is actually the freedom of this link to rotate around itself. Because of these spherical joints here, this link actually can rotate around itself, right? But this rotation around itself is changing nothing in the mechanism, so it's not translating any movement. And this is why this freedom is not changing the total freedom, and we have here extra, which is called the idle freedom. So you could have this kind of idle freedom that is not changing the mechanism, but it's extra freedom that mechanism, some links has it, and but it's that's why you can see it in the formula, but it's actually, it's not the degree of freedom, it's not considered in the total degree of freedom. And as I said at the beginning, is that when it comes to degrees of freedom, the first thing to look at is first, is it a closed loop? If yes, that has 1 degree of freedom. But if it's, even if it's not closed loop, it's open loop, but we have only 1 actuator that is connected to this mechanism, which means, let's say here, and this 1 actuator is enough to move the whole mechanism in a way it's supposed to move, then we have 1 degree of freedom. Okay, so here we comes to what is actually our focus in this course is robot arm. And here we have one. It's basically called the Stanford manipulator because it's developed by Stanford University. And here we see that we have the manipulator which has different joints. This basically is the first joint where we have, so this is the base, the frame. We have this, the red one can rotate around the first joint. This is the first joint actually, so this is the first link, sorry, second link, and there's between them the first rotation, which is joint 1. Then we have the second link here, which has also rotation between link 2 and link 1, represented by joint 2. So this is rotation. There is now actually, yeah, so there is a joint 3, which represents, so this whole, the green and blue is one link. Okay, there is no joint here. This is one link. Link 3 is the yellow one, which is sliding inside link 2. And here joint 3, which is prism. Then here we have basically joint 4, which is rotation between link 4 and link 3. We have joint 5, which is this kind of rotation between link 5 and link 4. And we have link 6 basically, which is another rotation. I will upload also a video to that, to mainly basically that mechanism, so you can see it. You can see basically the way it's moving, like I just described here. Now the question is how many degrees of freedom this robot arm has. The first thing that I would look at, especially when it comes to robot arm, is that, okay, how many joints I have. I have here 1, 2, joint 3, 4, 5, 6. That means this robot arm has 6 degrees of freedom, because not only I have 6 joints, I have 6 joints that they have only 1 degree of freedom each. Yeah. And if I also look at which is the same, how many actuators I have, they would have 6 actuators. That's why I have 6 degrees of freedom. But I can also apply the formula, and you would end up with actually 6 degrees of freedom. Okay. Now, so this is called manipulator, and what we have talked about now for spatial mechanisms is the mobility and degrees of freedom. Now we come to a new session actually, or a new topic, which is the forward kinematics. I talked in session 1 about the kinematics, which is the study of motion regards external forces. And this is basically kinematics itself. It has 2 topics. One is called forward kinematics and one is called inverse kinematic. Now, forward kinematics is representing the position of the target, or actually the model of the position of the target point. Let's say I have a manipulator like here. So manipulator is a robot arm. And we have a manipulator like here, and my reference for my target position of manipulator is always what is called the end effector, which is here. And the forward kinematic is a model of the position of this point with respect to the input rotational variables of the basically the joint of this, not rotational, sorry, the input variables of the joints in this manipulator, because we could have not the rotational, we could have sliding like here. So what the meaning of that, these joints, they are, as I said, in more like 99% of robot's arm, we have joints with 1 degree of freedom. That means these variables, like they are either, or this joint, they are either prism or revolute, and they have only 1 variable. So either theta, that representing rotation, or s, that representing